Good morning. The topic is non-singular and singular transformations. Starting with the definition of the non-singular transformation first. What is a non-singular transformation? T is a transformation from UF into VF. Then T is said to be non-singular if kernel T or null space of T consists of zero vector alone. This is very important. It consists of zero vector alone. That is, if I take an element alpha from this UF, then when applying the transformation, we get T alpha in V, right? And that will be equal to zero vector. That simply implies that alpha belonging to U and T alpha equal to 0 implies this alpha is 0, which means 0 vector maps to the 0 vector, right? If suppose we have alpha to be non-zero in this U, if a non-zero alpha belongs to U, and when applying T on this non-zero alpha, if this value is equal to 0, then we say that this T is singular. Please remember, for the non-singular transformation we have alpha to be 0, but for the singular transformation this alpha should be non-zero in this UF. UF means the vector space U over the field F, right? So the condition for the non-singular transformation is alpha belongs to U and T alpha equal to 0 implies alpha equal to 0. This is the condition for the non-singular transformation. Now coming to the singular transformation. So for the singular transformation, what would be the condition? If there exists, this is the sign for there exist. If there exists a non-zero vector, let's say alpha, belonging to UF, such that when applying the transformation on alpha, it is giving the value 0, then T is singular. I hope it is very clear now. Thank you. Okay, now few important theorems are there. If T is a linear transformation from U into V, then T is non-singular if and only if T carries each linearly independent subset of U this is the linearly independent subset of U onto a linearly independent subset of V. This is also the linearly independent subset but of V. That is, it is preserving the linearly independency and also mapping the bases to bases. Second, if T is a linear transformation from U into V, then T is non-singular if and only if T is 1, 1. Right? Okay, third one is for the finite dimensional vector spaces. Very important. For the finite dimensional vector spaces, let U and V be the finite dimensional vector spaces over the field F such that their dimensions are equal. If T is a linear transformation from U into F, then the following statements are equivalent. What are those? First one, T is invertible. Second, T is non-singular. Okay, what is the meaning of invertible? Invertible transformations means it is both 1, 1 and onto. And also it is satisfying the property T inverse equal to T inverse T equal to the identity operator. Right? So these are the two properties for the invertible transformations. Second, T is non-singular. Just now we have revised about the non-singular transformations, that is kernel T consists of the zero vector alone, right? Third one, the range of T is V. So here we are talking about the finite dimensional spaces. These are the conditions for the finite dimensional spaces, and these all are equivalent statements where the dimensions of U is equal to the dimensions of V, right? Then is if suppose alpha 1, alpha 2 up to alpha n be any basis for u, then T alpha 1, T alpha 2 up to T alpha n, these are the bases for V. So it is mapping basis to basis for the finite dimensional spaces. Okay, fifth one, if there is some basis, again let's say alpha 1, alpha 2 up to alpha n in V, such that T alpha 1, T alpha 2, T alpha 1, T alpha 2 up to T alpha n. This is a basis for V. Right? Okay. So these are very important statements. Do remember them. Next is the theorems for the invertible transformations. A linear transformation T on a finite dimensional vector space is invertible if and only if T is onto. Okay. Second, a linear transformation T on a finite dimensional vector space is invertible if and only if T is non-singular. So for the finite dimensional vector space, invertible transformations implies two things. T is non-singular and T is onto. But if the dimension is not finite, then invertible transformation implies T is 1, 1 also. Just now we have studied in the previous remarks. So invertible transformation becomes onto for the finite dimensional vector space, otherwise it is also 1, 1, and also for finite dimensional vector space T is non-singular. Let's move on to one example. If A is linear transformation on a vector space V such that it is given to us, this condition is given to us, then we have to prove that A is invertible. Now it is not given about the dimension to be finite or not. Just simply it is given that A is a linear transformation on a vector space V, right? We have to show that A is invertible. Invertible means we have to show that A is 1, 1. And also we have to show that A is onto. These are the two conditions for the invertible transformations. Okay, first we need to show that A is 1, 1. What is given to us? That A square minus A plus the identity operator is equal to the 0 vector. This can also be written as that A square minus A is equal to minus of the identity operator. Marking this as 1. So first we need to show that A is 1, 1. What is the condition for A to be 1, 1? So that is we have to show that if I take any two elements, let's say alpha 1 and alpha 2 from V, then what is the condition for 1, 1? Then A alpha 1 equal to A alpha 2 implies alpha 1 equal to alpha 2. This is the condition for 1, 1. So we have to take two elements from the vector space, and by using this we show that alpha 1 is equal to alpha 2. So let alpha 1, alpha 2 belongs to V. Then A alpha 1 is equal to A alpha 2 implies I can also take one more linear transformation on these two, because A is a linear transformation. If any alpha belongs to the vector space, then A alpha also belongs to that vector space. Right? It is given to us that A is a linear transformation on vector space V. So if any element belongs to V, then A alpha also belongs to V. A is a linear transformation from V onto V. Right? For any alpha belonging to V, A alpha belongs to again V, the same. Now as A alpha belongs to V, I can also write that again if I apply the transformation, then A of A alpha also belongs to V. Right? If I have A alpha 1 to be equal to A alpha 2, which means these two also belongs to V. So let me apply one time more the transformation A on this. Right? Okay, so this implies A square alpha 1 is equal to A square alpha 2. So let me mark this as 2 and this to be as 3. I'm going to subtract 2 and 3 together. Why? Because I'm having the condition here that A square minus A is equal to minus I. I have to use this condition. So that is why I'm going to subtract this 3 equation from 2 equation. So A square alpha 1 minus A alpha 1 is equal to A square alpha 2 minus A alpha 2. So this means A square minus A of alpha 1 is equal to A square minus A of alpha 2. Now what is A square minus A? It is minus identity operator. So writing here minus I alpha 1 equal to minus I alpha 2. Taking this in bracket. So this implies what? Okay, identity operator applying on alpha 1 implies I of alpha 1 is equal to alpha 1. So this is equal to minus alpha 2. So that simply implies alpha 1 is equal to alpha 2. So we have got that whenever we take two elements from V, then A alpha 1 equal to A alpha 2 implies alpha 1 equal to alpha 2. So this shows that A is 1, 1. So hence A is 1, 1. Now to show that A is on. So secondly we show that A is on 2. If A is a linear transformation from the vector space V onto itself, what is the condition for onto? For any element alpha belonging to this V, there must exist one element in this V such that T of this element is equal to alpha. This alpha. Right? This is the condition for onto. So let's take one element from V. So let's take alpha belonging to V. So this implies A alpha also belonging to V. From these two reasons, A is linear transformation. Right? So from these two, this implies that alpha minus A alpha also belongs to V. Reason, closure property of the linear transformation, right? Okay. So now I am going to apply the transformation on this element which is belonging to V. So A of alpha minus A alpha, right? So this is equal to A alpha minus A square alpha. That is A minus A square of alpha. A minus A square is, yes, A square minus A is minus I. So A minus A square will be simply I. So this is identity operator on alpha that gives the value to be alpha. And this alpha is certainly belonging to V. So this belongs to V. That means for alpha belonging to V, there exists this element which belongs to V such that A of this element belongs to V is equal to alpha. Right? So writing this, thus alpha belongs to V implies there exists alpha minus A alpha belonging to V, this element which is belonging to V such that A of this element is equal to alpha. So such that A of this element is equal to alpha, right? So this implies A is onto. So we have shown that A is 1, 1 and also A is on 2. This implies A is invertible, right? So A is invertible transformation. Okay, thank you. Stay blessed.